Yeah, I wanted to take a few minutes on the subject of like current sources, adjustable current sources and shit. To talk about, some of the circuits that, you see in some data books. This one, for example, could be done with 317s, and, but with the super expensive regulator they're using, which I don't know, I guess I'd have to look some of these up. I mean, some of those aren't that bad, unless you get them in TO3 packages, but it'll still run you a few bucks, so they're a lot more expensive than 317 is. Um, but anyway, in the circuit here, they have it so it'll do 0 to 3 amps, and they're using a 317 as a constant current source in and of itself, just so you can power another constant current source, but make it adjustable with a normal potentiometer, instead of some high wattage like 5 watt potentiometer or something, which is what it would take if you wanted to directly adjust the output current of one of these things. You do the math, you wouldn't believe, how many watts, you'll need to actually make like a 0 to 1 amp CCS on one of these things. I mean, in fact, let's do the math real quick. It's 1.25 volt drop, but let's say you wanted an amp across it. All right, so, basically, oh shit, that's 1.25 times 1 amp, so it's 1.25 watts, is the pot rating you need to have. So, you know, and that's to keep it within that. Now, the thing about it is, though, is that 1.25, 1 amp would have to be your pot rating at any setting. So, so we would need, a 1.25 ohm pot to do that, right? Okay. Which the good news is it's easier to find high wattage pots and low ohm values. But the thing about it is it's a matter of figuring out what its maximum rating is. So let's say we found a pot that was 1.25 ohms, all right. You know, and it was rated at 1.25 watts. Well, the thing is, that because of how you're using it, that 1.25 ohms would be the maximum resistance, right? So if you cut that resistance in half, what's going to happen? Basically, if you used it as a rheostat, you cut that resistance in half, your current's going to double, right? So, again, you really got to try to set it to the lowest value, not the highest value, for one thing. So, again, 1 amp is what you're going to be, after as a maximum current, not a minimum current. But the thing about it is that your pot has to be able to handle 1 amp through its wiper under all settings. So let's say we used 100. Well, let's say we used a 50 ohm pot. You might be able to find a pretty high power 50 ohm pot, within reason. So if you had 1.25 volts divided by 50 ohms, that would give you an output current of 25 milliamps. Okay, that would be your minimum current. Your maximum current would be 1 amp. But the thing is that it's got to be able to handle that. So basically, I squared R comes into play here. Okay, or V squared over R if you want to do it that way to figure out what your wattage is, because we know it's 1.25 volts, but so let's just deal with I squared R. So I squared is 1 amp, so it's 1 divided by 50, or times 50 rather. So that's a 50 watt potentiometer you need to do that. So you understand where I'm saying here, is that these things can get really out of control, so that's why it's worthwhile looking, for alternative ways of doing constant current sources that you can use just a real regular potentiometer that's maybe a half watt or something like that, instead of having to go with something ginormous. And this is one way to do that. They're using a 317 as a constant current source, but set at a really low current. So, in fact, you can calculate that. It's 1.2 volts divided by 120 ohms, so they're set at 10 milliamps, which 10 milliamps is what they kind of suggest is the minimum current flow through one of these things should be, okay? So, but they got it set as a 10 milliamp source, even though you can go lower, believe me, if you look. You can go much lower than that, because even that can become actually a burden if you're trying to make a 317 adjustable regulator and you're trying to find a pot that'll do it. Because even 10 milliamps can be a lot if you're dropping 20 volts across the thing, and you need a 5K pot to affect a full adjustment range. So yeah, I mean, you might have to go to Jamico or someplace that sells cheap higher powered pots, to get yourself a half watt or a or 3 watt pot even might be necessary sometimes. But depending on what you're doing. But at any rate, they're basically allowing you to use a low wattage pot, by loading this with a constant current source. But the caveat is it's got to go below ground, like -5 to -10 volts below ground. So you need like a triple output, 2 supply rails, one positive, one negative, to do this. But with a 317, you wouldn't want to adjust it over 0 to 3 amps. Obviously, you'd have to change these values. So it go over 0 to 1 amp or something like that. These things are current limited and stuff to some extent, but you still don't want to continuously drive it into that limit. You don't want to drive too much power through one of these things, even with really good heat sinking. Like I said, if you got a large voltage, this is operating over, and something like this, you might be in that situation. Well, you're just count on getting like half an amp or so out of it to be safe with good heat sinking. Because even forced air cooling is not going to help you. If you want to get 1.5 amps over a 30 volt range, I mean, it's just not going to be enough. But at any rate, this is an over elaborate way of doing it. Just think of this as a 317 instead. Because a simpler way to do it is just take a JFET and basically short the source to gate, okay, and just but get one of those lower current JFETs. Don't get one of those J111s. Get a lower current JFETs, about 5 milliamps or something like that, 5 to 10 milliamps, and you can just stick that on there as a constant current source. You're still going to have to tie it definitely below ground, a few volts, but the point is it'll do the same thing. Just make sure it can kind of handle the power, dissipation, of the voltage range you're going to be looking for. Otherwise, using the 317 is adequate too, because that can handle a lot of power. Okay, when you're talking 10 milliamp currents, I mean, it can handle a lot of power. You won't have to worry about that. So you won't go wrong doing it this way, but it's kind of overkill. There are other simpler ways of doing it that I've done. So, and you'll find some of those others in data sheets, depending on where you look. So, but at any rate, one of the key things to keep in mind here is this does produce 0 to 3 amps. Now, why is 0 a big deal? Because, if you just ran this like a regular regulator, like I did on this circuit here, this is a regular regulator. The thing is, you'll never get it down to 0 amps because the 317 needs, a few milliamps to operate, realistically. Even though if you look at the data sheet, it's actually less than a milliamp. But it will still never get down to 0 current, regardless of how you think of it. But again, in practice, I think you can get it down to a milliamp or two. But it'll still never be quite 0. So if you really need 0 or really low currents, as a constant current source, like you're driving a photodiode or something like that, you don't want too much current flowing through it. Well, you want to be able to get it down to 0, because even this won't go down to 0. I mean, even if you use the right components, unlike the ones they used here, which aren't adequate, you're going to tinker with it to actually get this down to, like it says in the article up here. I couldn't get mine below 100 and something milliamps with the exact values they chose, but I believe it can work, fully, with judicious selection of components and maybe an extra resistor here. But it still won't go down to 0 amps. Now, This circuit over here, because they are referencing it below ground, could go down to 0 amps, because that, this is acting like its minimal current load by putting this constant current source here. Since it's sinking that down to below ground, well, that'll take care of the 1 to 5 or 10 milliamps or whatever you might need, in order to keep this regulator functioning. Even with no load on it, it'll still actually be on. Whereas that other circuit, like I said, the one we just looked at there, if you take the load off, well, there's no power to it. That's the only source of power is through the load. Well, this will be continuously powered, which, which is fine and dandy. I mean, the voltage will still float high, it doesn't matter, but it'll always be on. But because of this, it doesn't have to sink its minimum current through the load. It can sink it through this constant current source. So that's the advantage here. So if you add a load to it, this is going to be part of your current sink. So again, the lower you keep it, the better. But, it's still not going to affect your load and the current going through your load. So, with the exception that it's being shared with this thing a little bit. The current you may think you're getting out of here is part of it's going through here, but a very small amount. Again, really, with something like this, you probably wouldn't have to do more than a milliamp or so, a milliamp or two. But again, with a JFET or whatnot, you're going to be, 4 or 5 milliamps, which is fine. But the point is, you'll still have a good regulated load, and this won't really affect the current going through it that much. So it's, but it'll work, and you can go down to 0 amps because of the fact that your load is on a separate reference, on a ground reference. This is going below ground, so it can pull this output clear down to ground, without there being an issue. So, and ostensibly, it can even pull it below ground. I'm not really sure about that. I might go ahead and build this thing up. I haven't decided. I'm chewing on it right now because I don't know if I want to mess with the dual supplies and everything right now. I'm kind of dual supplied out. But another little interesting circuit too is this, and again, I've done this before too in many variations in practice, as opposed to just cobbling things on a breadboard. But the same principle applies. I mean, they're taking a voltage regulator, and so it can go down to 0 to 30 volts. Normally this would be 1.2 to 30 volts, if you just use ground as your reference. But because they're pulling at 1.2 diode voltage drops below this, and they're saying a LM385, you don't need that. Just really, I would recommend at least one just regular diode, if not maybe two. But the point is that, yeah, you're having to use a dual supply, but you can use a charge pump or something like this, because the amount of current, is not that much. And I've seen people use things like charge pumps and some other little tricks they play with the voltage regulators to generate a slight negative voltage for this, of 2 or 3 volts. And that's all you need, to actually bias this thing so you can go below 1.25 volts on your output. So, because otherwise you're limited by, that adjustment terminal, that 1.25 volts. That's the minimum you can go with respect to ground, unless you're referencing something below ground. So, and the technique does basically work. So, again, tinker with it yourself before you solder it into a circuit board, but, to make sure it's working like you want it to. But it is a workable deal. I mean, I can tell you that by experience. This stuff is all straight out of a data book here. So, this has always been a curious circuit. I still haven't figured quite out what they're doing here, because these regulators are all the same. So, I know a source regulator is not meant to sink current, so I'm not sure what they're doing here. I don't know if this is supposed to be a third ground terminal, and you got like plus 20, you got like a center tap transformer hooked to this, or not. I mean, I'm not really sure. I'm going to have to do some research into that, because these regulators are not supposed to sink current, but they would have to sink current if you had a positive going signal, and this was your neutral, your other transformer terminal that was your reference. Well, you got current going out of this regulator and then coming down and going back into this one. Well, that means it would have to sync current somehow. So I'm not really sure. I've got to, check that out. Just out of curiosity, I've got to do that. Oh, and this is one example of a circuit that could be used with what we were talking about earlier. This is from Elliott Sound Products site too, by the way. But you can find this circuit all over the damn place. It's basically a 555 charge pump. So, and they're generating a negative voltage with it. But, again, and this could supply the kind of 5 or 10 milliamps you might need to act as a reference. So you could build a little circuit like this. It's a little elaborate. But, you could build a little charge pump like that. And that's a negative charge pump. But, there's also a positive one you can do. And here, this says Projects 248 HTML or whatever, if you want to go check that out. And this is something, I actually happen to have some of these in stock. I'm really curious about this 300 volt amplifier. So, clearly with 1 mega ohm of resistance, it's very limited in current, but, it uses, one of those transconductance op amps, and I'm definitely curious to just build one of these to see what happens, although I'm probably not going to power it for more than 50 volts, but, apparently these things are obsolete, and you can't, buy transconductance op amps anymore from what I've heard, but I don't know if that's true or not. I'm sure there's some surface mount version of some of this stuff, but they've kind of have been on the way of the dinosaurs, for what they're originally used for. Now, tracking regulators are interesting, and Elliott Sound Products actually in some of his power supply pages talks about, and again, I'm not affiliated with Elliott Sound Products, but he actually talks about tracking regulators and super regulators, and the fact right here is again one of his pages talking about super regulators, and the idea is having two regulators in series, and he likes 317s because they're lower noise than other 3-terminal regulators in the 78 series anyway. And the whole point is is creating a low ripple power supply, and if you use 2 regulators, again, keeping in mind that one of them has to be higher voltage than the dropout voltage of your next regulator in series. But in theory, you're getting that gain, that ripple rejection and all that shit times 2. So you could actually make a better regulator. And then if you put a pi filter, an LC pi filter on it, like he talks about somewhere in here, you even get better ripple rejection. So you can make really a fairly quiet, very low ripple power supply doing things like that. And because I always wondered, you see these in data books all the time, tracking pre-regulator. What the fuck's that for? I don't know. They never tell you anything. It's a data book. They don't explain what it means. So, but this is kind of what it is, and this happens to be an adjustable output version. Again, use a 317, not a 117. Good luck finding that's like a military spec part or some shit. They always try to push on you, but you never find out where to buy them. You couldn't afford it. But again, this output of this one has to be, the input of this one has to be a higher voltage than its output by a few volts, and that has to be higher than the output you're ultimately after by a few volts. So you're looking at 5 or 6 volt drop across these things. But the point is, if you get that benefit of a really low ripple power supply and stuff like that, hey, it could be useful. And again, I got most of these circuits are from data. This is definitely from a data book. Again, I already discussed that one, and because again, I don't know how many, if any, more of these I'm going to build. I'll probably build that one. I'll probably build that one just for curiosity. Like I said, this one I got to look over and figure out what. I don't think this is very useful. It's in theory, it's sort of a way of making your own variable AC power supply for what that's worth. But it's just kind of an oddball circuit. It's always caught my eye every time I saw this in a data sheet. I always thought it'd be kind of interesting to do it, but I would need an actual. I don't think Analog Discovery could probably handle. Sine wave would probably handle this very well. Because I think it would. It might, again, if I really push the extremes on current, I might be able to get it to actually work. to trick it into working. But I don't know. I'm gonna have to look at it. But I don't think it's very useful right off the top of my head. It's just a curiosity to be able to adjust both sides. To act like a dual clipper like it is. It's just curious to do that with regulators because theoretically I can handle some current, right? So if you needed to adjust the AC input, because this actually, if you fed this through a bridge rectifier and a filter, the filter would actually respond better to this waveform than this waveform, even though this is probably going to have worse harmonics in it. Still, without having that peak in there, that will really reduce your ripple current, to your capacitors. So maybe you could use some lower quality capacitors or something with it. Fuck, I don't know. It's just an interesting curiosity, is what it is. So, I might take a look at it. And this was something out of one of my, I call it the pink book. No, this is out of the green book, actually. I'm sorry. Which is another really good book that I have that, is certainly way out of print. This was, because I did an earlier video, I did an AM transmitter, which is basically a mixer circuit, just like this, but but it involved a bunch of inductors and crap like this. This is doing it just with a transistor, and some capacitors, a single transistor. The other one required two transistors, a bunch of chokes. That was out of Hazen's textbook. I was just kind of curious to build this up and see if it worked, So, anyway, I might get to that and make follow-up videos if I do. I'm still deciding. I'm just about so circuited out. I feel like taking a break from some of this shit for a while. But at any rate, I just wanted to at least cover some of that theory there. Just to give you some insight and to show you that looking through datasheet example circuits, there's some interesting shit in there. If you do some digging, there's a lot more than what I showed you here. Just any data sheet, and remember, different manufacturers have different example circuits typically. But sometimes you'll find like the mother load, and two, realize this: data sheets have different publication dates even for the same part number. Sometimes it might pay to go back and find older publications of the same data sheet, so you might find some surprises in there. So anyway, you can find some interesting shit in data sheets, if they happen to have example circuits. So anyway, that wraps it up for this. Cheers.